This video will walk you through Lesson 5 of Unit 5, which will teach you how to find all rational zeros of a polynomial function. First thing I'm going to show you here are how to find the possible zeros of a function using the old-fashioned way, which is using the rational zero theorem, basically trying to figure out what the possibilities are without using a graphing calculator. But the majority of the lesson will teach you how to use your graphing calculator and what you've learned this chapter and in previous chapters in terms of your other algebra skills and how to find these different zero values. So let's talk about first how people used to find rational zeros the old-fashioned way. Before graphing calculators could calculate all kinds of stuff, the rational zero theorem basically says if you know the factors of the constant term and you know the factors of the leading coefficient, you can combine those together in a fraction to figure out all kinds of different possibilities that the zeros could be. So instead of just kind of guessing and checking an infinite amount of numbers to plug in for x to see what comes out to zero, we can at least narrow it down by figuring out two things: the factors of the leading coefficient and dividing that by the factors of the constant term divided by the factors of the leading coefficient. So let's look at the two examples here underneath to just find the possible rational zeros. We're not going to necessarily find the actual zeros here. We're just going to find all the possibilities. So to find the possibilities here, if we look at 1a, first thing we need to do is identify what is the constant over what is the leading coefficient. So our constant, if you look at the problem here, is 12. The constant is the term without the x. The leading coefficient is 1 because our leading term is x cubed. Leading coefficient would be 1. So what I'm going to do here is list out all the factors of each of these numbers. So again, factors are simply numbers that divide evenly into any given number. So with 12, we have 6 total factors that'll work. And each of these factors, we can have both the positive and negative version because there are combinations where you have 2 positives, 2 negatives that will work out very nicely. So the numbers that divide into 12, we have positive and negative 1, positive and negative 2, positive negative 3, positive negative 4, positive negative 6, and positive negative 12. When you have a leading coefficient of 1, makes it real simple. There's only one thing that divides into that. Well, I guess technically two things. Positive and negative 1, though. It's only one digit, if you will. All you do here to figure out the rational zeros is you take every term from the top divided by every term in the bottom. Since everything would be divided by positive or negative 1, you would end up with the same 6 terms you had in the numerator. So your possible zeros would be positive or negative 1, positive and negative 2, so on and so forth here with the rest of this list. Because again, dividing by 1 doesn't really change the value of the numerator terms. So what this big list means is there are 12 possibilities here for the zeros of this function. So again, before the days of the graphing calculator, you would take each of those 12 numbers, plug them in for x, and figure out which ones, using trial and error here, plug and chug, figure out which ones spit out a result of 0. It's inefficient, but at least this method would narrow it down so you're not just blindly picking numbers all over the place and having to guess and check completely your whole way through it. Example B, same idea. If I want to figure out the possible zeros, once again, I'm going to identify the constant, which is negative 10, and the leading coefficient, which is 4. It doesn't matter if your constants and coefficients are positive or negative. You'll still use plus and minus with each of your factors. That doesn't matter. So what factors do we have for negative 10? 4 factors here. Positive and negative 1, positive and negative 2, positive and negative 5, and positive and negative 10. For coefficient here, leading coefficient of 4, you have positive and negative 1, 2, and 4. Those 3 numbers will divide into that. So with this here, once again, you're going to take every term from the numerator divided by every term in the denominator and make your list. So everything here, I'm going to take all the numbers from the top divided by positive and negative 1. So I'll keep everything here the same from the numerator. That makes it easy to start. Now I'm going to take all those same numerator values divided by the positive and negative 2. So I would start with 1 over 2, gets me 1/2. 2 over 2 gets me 1. I already have it in my list, so I'm not going to list it again. That's redundant. 5 over 2, well, that's new. 10 over 2 just becomes 5. I already have that, so I'm not going to list it again. Now I continue to take that same list of numerators divided by the positive and negative 4. So We go ahead 1 over 4, that would be new. 2 over 4 is the same as 1/2. I already have that. 5 over 4 would be new. And then 10 over 4 is the same as 5 over 2. I already have that, so I am finished. So here I have 16 possibilities that I could plug into this function. A handful of those will end up being zeros. Again, though, this is a pretty inefficient way to figure it out. It does narrow down your answers, but again, it's a lot of plugging and chugging to figure out which ones work and which ones don't. So what we are going to do to figure this out is we're going to shorten the process up a little bit by using our graphing calculators to give us an idea as to where the zeros should be, and use our ability to A, synthetically divide, and B, factor to go ahead and figure out what solutions we should have. So let's go ahead in the next handful of examples here. We're going to take a look at how do we find these zeros. So let's take a look here at example number 2. So we're going to find all the real zeros of the function that's given. So what we're going to do here first is we are going to use our graphing calculator to punch stuff in and figure out where the zeros should be. So we go to our graphing calculator. We know by this point how to punch everything in. So go to your y equals menu. And we're going to go ahead and type in our entire function. Again, making sure that we're using all the right signs. We're making sure our exponents are in the right spot, etc., etc. So you can see here how I'm typing everything in. Make sure our function's correct. We're going to do 2 things here. We're going to take a look at the graph. So you'll notice in this case that our graph kind of seems to go off our screen, off our 10 by 10 screen, and that's fine. We're not using this to find mins and maxes. We're trying to figure out where the zeros are located. Remember, the word zero is a synonym for x-intercept. So I'm looking to see where the graph either touches or crosses the x-axis. You can see in this graph it crosses it at 3 different points. Now, you can make some good solid guesses from where those 3 zeros occur just by looking at the picture here. And the nice thing about some of these problems is that they will cross at very nice points. The other thing you can do is use your table. So I can go second graph, get to my table. If you want to find your x-intercepts from your table, remember, the x-intercept means y has to be 0. And you can see here in this table, we've got 3 distinct places that we're going to see our values here. -1, 0, 4, 0, and 5, 0. Now, theoretically, could you just list them out and say those are my zeros? Sure. However, not all the zeros you're going to find throughout these next couple of lessons here, they're not always going to be at nice integer numbers. They may not also be real numbers. They may also be imaginary. So we do need to verify by algebra that these zeros actually work the way they're supposed to. And more so that when you get messier numbers, you get the imaginaries or things like that, you know how to go about and solve them. So we start with these nice integer numbers here because the math is cleaner, it's easier to verify. So here's our process to figure this stuff out. So you can use either the picture of your graph or the table from your calculator, it doesn't matter which. You need to pick any of the zeros that actually work. Does not matter which one, just pick one that's nice and clean that you can use. So let's go ahead and look at taking -1. Okay, so let's go ahead and use the zero of -1. We know that's a 0. We're going to use that to do some synthetic division. So I'm going to go ahead and put that in the box. Look at your function. Make sure you don't need any placeholders, just like we talked about back when you learned synthetic division in the first place. It doesn't look like I need any placeholders here, so I'm going to go ahead and write out all of my coefficients and constants. And now we're going to go ahead and do some math. So we pull down the 1, multiply by what's in the box, add the column. Multiply that result by what's in the box, add the column. Multiply, add. The beauty of these having to be zeros, your remainder will always be 0 every single time if they are indeed zeros of the graph. Because what ends up happening is these result in the factors that would have to divide in evenly. So you learned how to do that with synthetic division when we did factoring problems. These are kind of the same idea. If you have no remainder, that's a good thing. If you do have a remainder, it means you either pulled the wrong number or you did some bad math in your synthetic division process. Once we do the synthetic division process, we're going to take the numbers that are left here and write an expression. So as you may remember, the last number, as we talked about, is your remainder. Second to last is your constant, and then you work your way backwards. X squared, and then if there's more numbers, you would obviously go up the x ladder, if you will. So really we have an expression here of x squared minus 9x plus 20. Once we get this expression, we are going to go ahead and use factoring to split this apart and use those factors to go find the zeros. So you can go ahead and use your little diamond method if you wish, or just go ahead and do it in your head. It doesn't really matter which. But remember, your goal is to add to the b value, that's negative 9, multiply to 8 times c, so 1 times 20, which is 20. The two numbers that will do that are negative 5, negative 4. When you have a factoring problem that has just a regular x squared, we can simplify the factoring. We don't have to do a bunch of steps here to break this down. We can just simply go ahead and write our two factors, x minus 5, x minus 4. Now, if the problem was just straight up, let's go ahead and factor, we're in great shape. But it says to find the zeros. So we're going to go one step further, and you can write it out or do this in your head. We're going to take each of those factors and set them equal to 0. So, x minus 5 would equal 0, x minus 4 equals 0. Here's what that means. I would get a final answer for my zeros. X would have to equal 5, 4, and we originally started with that negative 1. Just like the factoring problems you did in the last lesson, you pull that down as part of your answer, and here you have your list of zeros as a final answer. If you look at the result from your calculator, so you have the zeros that are listed there. If we take a very quick look here at the calculator, you can see the three answers that we have there. Negative 1, 4, and 5. You look at your graph. Look where it crosses. Negative 1, 4, and 5 on your axis. So it verifies by all the algebra. It matches your picture. It matches the table in your graph. Life is good. So that's how you go ahead and verify, find your zeros given a large function like this where you have something that starts with an x cubed or greater. The example underneath, you can find the answer for in the answer key note packet that I have online on Schoology. Feel free to try that on your own. However, I do want to show you one more example here on the next page of your notes because we're going to go ahead and move up a degree, and I want to show you the process for how to solve that. So, if you take a look at the next page here, I'm also going to go ahead and change the example from what you have in your note packet because this particular problem here, while it does work, very messy answers, and quite honestly, not worth it. So what I'm going to do is go ahead and change this function, and you should do the same thing if you haven't already. We're going to change this function to 2x to the 4th minus 9x cubed plus 37x minus 30. So in this case here, we are going to have a polynomial function that's a quartic. It's going to the 4th power here. Now we're going to go ahead and do the exact same process we did before. So we're going to go ahead and punch this into our calculator and work through the different steps that we need to in figuring these things out. So using your calculator, you're going to go ahead and punch the different things in here. So what you'll notice is you will have a crossing at a few different places here. Some places it's going to look really nice and clean. Some places not so much. You, again, want to pick a 0 from your calculator that's nice and clean so we can start doing a synthetic division process. So one of the zeros that you can pull from that synthetic division process is there's a 0 at negative 2. And you should see that on your calculator as well. So when we do synthetic division here, if you notice your function, there's something very, very important here. You need to remember placeholders, as I referenced in the last problem. So big placeholder alert right here. You look at the given function. Now, this doesn't affect the graph of it. You don't have to have all the exponents in descending order here. But when you do synthetic division, you have to, otherwise it's not going to work. The part of the problem that's missing is the x squared term. So what we can do is we can rewrite this function with a 0x squared, so that way we have all of the correct exponents in descending order, which will allow us to do synthetic division correctly. So we'll go ahead and rip off those coefficients. So we'll have a 2, negative 9, a 0, a 37, and a negative 30. So we're going to go ahead once again, and we are going to do our synthetic division process. So we pull down the first number, multiply by what's in the box, add the column. We multiply by what's in the box, add the column. We multiply by what's in the box, add the column. Multiply by what's in the box, add the column. And guess what? We have ourselves a remainder of 0, which means we are in really good shape for the math we've done so far. So, once I've done that, I'm going to go ahead and take the results that are there, write an expression based off of that. So, once again, last term's the remainder, second to last is our constant, x squared, x cubed. So, that means we have 2x cubed minus 13x squared plus 26x minus 15. Now, that in itself is a fine problem, but my goal is I want to be able to factor this. The thing is, there's no really great way to factor something that's a cubic. So in this instance here, if when you do your synthetic division, you're down to a cube, that's great. You're going to want to do synthetic division again to get it down to something that's a quadratic, aka something with a squared, because that's going to allow you to use your trinomial factoring strategies. So you're going to go back to your calculator and look for another one of the zeros. The next zero I see is a positive 1. So I'm going to go ahead and use the coefficients from this new problem and keep working it through. So again, using the 0 of 1, I'm going to go ahead and do the same pattern here so you can see how I'm filling in my table. Once again, I get a remainder of 0, which is a good thing. And now I'm left with, we have an x squared, an x, a constant, and my remainder. Which means I have the following. I have 2x squared minus 11x plus 15. Once we get it to a quadratic, we have a trinomial, a quadratic trinomial here. We have an x squared, 3 terms, great. This is now something we can factor so we can so we can find the rest of the zeros. So I'm going to go ahead here and factor this apart using our diamond. So again, what adds to b multiplies to a times c. So a times c in this case, 2 times 15 is 30. We're trying to add to negative 11, multiply to 30. Two numbers that do that, negative 6, negative 5. The one thing you have to be careful with, and you have to remember, when factoring a trinomial that's got a number in front of the x squared, so something that's not a 1, we have to set this up a little bit differently so our factors are correct. So, I'm going to go ahead and replace that negative 11x with a negative 6 and a negative 5x in the middle. I'm going to keep the 2 terms around it, the 2x squared and the 15. I'm going to bookend them, keep them the same as part of my problem. We group each half of the problem, and we find the GCF of each group. So first group, I can take out a 2x with an x minus 3. Then I can take out a negative 5 with an x minus 3. What that means is I can rewrite my factors as 2x minus 5 and x minus 3. Now we get to the grand finale. It's broken down as much as possible. Now we can go establish what our zeros are. So we know that negative 2 and 1 are zeros because we've used those in our synthetic division. Awesome. Based on my two factors here, so again, in your head, x minus 3 equals 0. Well, x would have to be 3. 2x minus 5 equals 0. Add the 5, divide by 2 to get x by itself. Your final 0 would be 5 over 2, 5 halves. That is not something you're going to see in your table on the graphing calculator. Now, you can kind of try to eyeball it from the picture, but there's no great way to say for sure it's at 5 halves on the x-axis. So part of this process does allow you to figure out fractional or other types of zeros that aren't exactly integers. So that's why we do kind of go through this process, as lengthy as it is. But what you should hopefully see is that it's all math you have learned and you've practiced several times over. It's just another way to use it to work with another concept. So, in summary here, we're finding zeros of the function. We're not going in blind with this. You're going to use your graphing calculator to get an idea as to what the zeros should be. You're going to verify using algebra what they are. The way that you do that is you start with synthetic division, get it down to something where you have an expression that starts with an x squared term, and then we use that to factor apart to get the remaining amount of our zeros. So that's how you go ahead and find rational zeros using your graphing calculator and using your algebra skills. The last example that's underneath that, again, you can find the answer key for on Schoology in the no packet answer key. The last problem, once again, it's really gross with the numbers that are originally there. If you would like to try it, this is the function that you will see in my answer key. So g of x equals 2x cubed plus 5x squared minus 11x minus 14. It goes through the same type of process you saw with the last problem. It's a little bit shorter because it's a power of 3, so you don't have to synthetically divide multiple times, but you'll see it's kind of a similar idea when you get to the factoring part, given the leading coefficients. So you can feel free to try that on your own. Check it with the answer key that is online. Once again, this video here helps you find rational zeros using your graphing calculator, synthetic division, and factoring.